So I recently completed my PhD from UC San Diego, and most of the work I will be presenting today is done with the collaboration with AMD, even though I'm joining NVIDIA now. So I will be talking about, I worked on both memory and compute for reliability. I will be focusing on reliability for heterogeneous memory, and whenever you try to optimize for reliability, you lose some performance. So the goal is to lose as less performance as possible, improving reliability. Same is the case with security. When you try to improve security, you lose some performance. So let me start with an observation I made very recently. So this is a car insurance policy. It's in Portuguese, so let me translate it for you. It says that car accidents happening because of ionizing radiations will not be covered in this policy. So basically it means any transient faults will not be covered in this policy. So this means that errors in computer systems are affecting the end users, and such errors are only going to increase, and the reason for that is technology scaling. We are shrinking the constituting components of our computer systems. We started with 90, I don't know before that, and then 32 we have 9, and Intel is coming up with 7. And when you're talking so small, now the constituting components like transistors are just few atom thick, and any slight variation in process or operating conditions like voltage, temperature or frequency can lead to faults, and these faults manifest as errors in the higher layer. There are many possible effects of technology scaling in terms of reliability. I will be focusing on aging and voltage droops. You can also call it single event upsets. So while aging creates permanent faults, these called transient faults. Like permanent faults will stay there and they return the wrong value every single time. Transient faults stay while the fluctuation stays and then they go away. Technology scaling also has an effect on emerging architectures, as the previous talks have pointed out. Gone are the days when we were able to speed up a single CPU and were able to extract more and more performance every year by cranking up the frequency. So when we lost that, we came to multi-cores. Only way to get more performance is to run more things in parallel, and now we have GPUs which can run millions and thousands of threads in parallel. So when you run so many threads in parallel, it's not your compute that's the bottleneck. You have a lot of compute, but you need to feed that compute data to process it. If it won't find the data, it will be just lying idle. So the memory bandwidth becomes the problem, as the first talk pointed out today as well. And to satisfy that bandwidth demand, there are new memory technologies that are coming in, 3D die stack memories. So these memories can provide you higher bandwidth, and they have, like AMD has HBM, NVIDIA is using HBM, Intel has Micron, Samsung has wide I/O. So these memories, they are based off DRAM chips, but they are arranged differently and they can provide higher bandwidth. The point to note here is both these have still the same latency. Not both these, 3D die stack memories and off-chip DDRs, they have same latency. The amount of time they take to get the bit is the same, but 3D die stack memory can get you more bits in the same amount of time. So that's what it's shown here. The same slide was there in the morning as well, that we have 6 to 8 times higher bandwidth compared to off-package DDR3 or 4 using 3D die stack memory. They are arranged differently, and the way they communicate is through silicon vias. They can transmit these bits using these new I/O channels. So which also means that there are new ways to fail. These TSVs can fail. Other than these are the new structures, so they can fail as well. These chips are going into highly critical domains. For example, GPUs with HBMs, high bandwidth memory, 3D die stack memory, were not meant to go for high performance computing. They were meant for gaming, where a bit flip here and there doesn't matter. but when they go run long scientific jobs, bit flip can be disastrous. And here, when they are going into autonomous vehicles for detection and machine learning and deep learning algorithms, here, even though they are rare, the consequences of these errors are life-threatening. The point is that reliability is important. Also, these errors, even though they seem like they are very, very small, like per chip, and they don't matter when we are using a laptop at home. If it crashes once a month, it's fine. However, these failure rates add up for large-scale systems. Like for example, a single DRAM chip, and I will show you the numbers later, might have a very small error rate or fault rate. However, when you have 1 million DRAM devices in a data center, somebody will have to go in every 6 hours to replace the bad DIMM. So the point of this work is, as memories are evolving, we do have hardware techniques, but some of these emerging memories, they have weaker reliability standards for now. And they will, like for 3D dissect memory, they will remain behind the conventional memories because they are in the market for so long. So what I worked on my thesis is, I focused on reliability, and I took reliability as a challenge. Although they have solutions in hardware, however, I focused if we can do something in software, and I focus on coming up with low-cost software-based solutions to detect, recover, and prevent such errors in both compute and memory. In this talk, I will be focusing on memory and how can we proactively prevent such errors in memory. So, also, why memory? I mean, in high-performance computing, we have a very big obsession to compute, but most of our computer is in fact memory, and the probability of a bit upset is proportional to the amount of bits you have, which is in the memory. So now that we have some motivation, I will flash you the outline. I was informed, or I saw online, that most of the audience will be undergrad, so I will have some backgrounds. And then I will talk about permanent faults and transient faults, and I will talk about reliability and performance. So I will be using faults and errors a lot, so let's get on the same page. Faults are underlying cause of an hardware failure, and a fault can be permanent or it can be transient. A permanent fault is basically which is returning a wrong value every single time, a stuck a bit, for example. And a transient fault is like a soft error or a single event upset or a particle strike that could flip the voltage in your cell such that a 0 becomes 1 or a 1 becomes 0. So these faults manifest as errors in software. So when I talk about error, it's what is coming to the software. A fault might not result in an error. It can be detected and or corrected, for example, error correcting codes. Or it might not be detected at all. Like for example, if you have a fault in your branch predictor unit, it's not going to show up in your software. It's only going to degrade your performance, and you will not notice that fault. Does that make sense? So, and there are many ways to measure failure, like mean time to failure, mean time before failure, but I will be using FIT, and that's what large-scale systems use because it's just an inverse of MTTF, and the good thing about it is when you scale the system, the FIT adds up, so it makes the math easier. So to define, FIT is just a measure to quantify system reliability, and one FIT corresponds to like one failure per billion hour of operation. That is so many years. However, for your data center, which has 18,000 nodes, close to 9,000 nodes, one FIT means that there is a failure every 12.8 years. And when you come to DIMMs, you have so many DIMMs, that means 1.6. One FIT means that you have a failure every 1.6 years. and when you go to chips, it means every 36 days. That was one fit, but let's take a look at the real numbers. So a socket fit rate of Celios is 1000, which is 2.3 days, and a DRAM chip, the fit rate is 35, that is every day a DRAM chip is failing.
So, a socket failure, does that every 2.5 days there is a socket failure?
Yeah, I mean, I picked these numbers from Celio's field study data, and that's what they said. Um, so yes, a socket is failing every 2.3 days. It could be different components in that socket though. So uh, in my PhD, I worked on permanent faults and transient faults, and I will be talking about part of which, if you want to read the full paper, MEMS is, and the second part will be in HPCA. So let me start with the first part. I will be briefly describing heterogeneous memory architectures, and then our system configuration evaluation, and we'll discuss some of the things from those results. So as it has been themed, like we want to solve this, we want to feed more data. So we are coming up with new memories, but we cannot give up DDR because it can fulfill capacity. 3D die-stack memory is good, but you only can get like 2 gigabytes until 2 years back. NVIDIA is now using 16 gigabyte, even which is less. So off chip, you need to have like a 256 gigabyte each node. So you have multiple memory modules in the same system to satisfy different needs. For example, an HMA system could be you have an HBM as your 3D die-stack memory, and you have an off-chip DDRX memory, 3 or 4, whichever you would like to, whichever your cost permits. And most of the research in these heterogeneous memory architectures only focusing on performance. And I would say this was the first time we thought of like doing it in software. Like people are working on improving the hardware RAS, reliability, availability, serviceability of HBMs, but doing it in software, I think this was the first attempt, as far as I know. So we study reliability and performance of these systems and how can we improve them in software. So this is the system I used. So we used a multi-core with GPU and caches, and then we used a high bandwidth memory. It's like version 2, HBM-V2, which has SecDed, which is single bit error correct and double bit error detect. And DDR3 is with chip kill, which can do symbol bit correction. So while HBM can only correct single bits, DDR with chip kill can correct multi-bit errors. It's a symbol-based technique, and you need 4x chips for that. The reason you cannot implement chip kill on HBM directly is because of the structural reasons. You need some sort of redundancy to implement chip kill. Like you saw in the morning, the cache line was coming from multiple chips. So you have a spatial redundancy in that case. While to have more bandwidth in HBM, each chip can provide you a cache line, so you can fire them in parallel and get, say, suppose 8 cache line together in the same amount of time. So that's why HBM gives you higher bandwidth, and the way chip kill is implemented cannot be directly translated to HBM. So we have a higher bandwidth memory which has newer types of fault rates like TSVs, which has higher density. That means more bits per unit area, so that means they can fail quickly, and it has a weaker error correcting code. While the off chip is low bandwidth, but it is very highly reliable. So we saw that there is a trade-off, and we can exploit this excess of heterogeneity in software to do something better. So before I go into results, there are a few definitions I would like to share. Access ratio is the number of accesses going to your HBM memory, 3D die-stacked high bandwidth memory, versus the total number of accesses going to the memory after cache filtering. So these are the requests which are going to the memory. And failure probability, or FIT, which I introduced earlier, at any point in time like as the device ages, this time is basically the device is aging, and the failure probability of my memory system is equal to is weighted by the failure probability is an addition of failure probability of individual memories weighted by the access ratio. So what this equation is saying, if I'm spending more time in HBM, the failure probability of HBM is going to govern my final failure probability. If I'm spending more time in DDR, my final failure probability will be governed by the DDR's failure probability. So we used these fit rate data from the Jaguar cluster, which for both we didn't need it for socket, but we used it from Jaguar cluster, which has 2.69 million DRAM chips. For fault simulations, we use fault sim, which can simulate different memory types and different ECCs, and it can tell you what would be the resultant fit when you apply these ECCs. So what you feed this memory simulator is raw fit rate of the system, and then you can mention, okay, this ECC to this memory type, and then it will give you a fault rate, and it's by AMD and it's public, so you can use it for your research. For performance simulations, I use Remulator, which is also public, and we selected 3 different kinds of workload: high bandwidth, medium bandwidth, and low bandwidth. The reason for that is both the HBM and DDR, they have same latency, it's the bandwidth. So if your workload is not that bandwidth intensive, it might not be a good idea to use HBM because they both have similar latencies. So here is the first graph. I will let you stare at it for some time. And what I call it is a failure surface, and it's showing you the failure probability of your heterogeneous memory architecture, which we considered, and how the failure probability is varying with access ratio and time as the system ages. So this is 0 to 350, basically 7-year lifespan of a node in a large scale system. So what it's saying is that failure probability is increasing as the access ratio is increasing, because you're spending more and more time in lower reliability memory. And failure probability is increasing as the system ages because it's accumulating more and more permanent faults. However, a thing to notice is that access ratio increasing access ratio doesn't increase the failure probability as much in the initial weeks, as much it increases it more in the final weeks. And the reason for that is, in the initial weeks, both chip kill and sec dead are equally effective because system is new, there are no permanent faults that have been accumulated, and any fault is not visible in the software. Any fault is not coming as an uncorrectable error in software, and both chip kill and sec dead are equally effective. However, when the system ages and it accumulates permanent faults, any new permanent or transient fault might lead into a multi-bit fault, which is outside the scope of correction of a single bit correction, sec dead, while chip kill is still effective. So what we propose is maybe have an access ratio control mechanism. In the initial week, you can be aggressive and you can use more and more HBM, but as your system ages, to maintain a certain failure probability, you probably want to crank down your amount of data or amount of access is going to HBM. If you don't want to go in every 2 hours to replace a DIMM and maybe delay it a little more. So any questions? But it's not, so the takeaway from this is failure probability of an HMA system when left uncontrolled can degrade up to 1000x from initial year to the final year. But it's not just the failure probability that we are concerned about. We want to see the effect of access ratio or using HBM on performance. So for that, we use Remulator to do performance experiments, and you see that we are varying the access ratio from 0 to 1, that is only DDR to only HBM, and this is performance IPC, instructions per cycle. And you see, as the access ratio increases, your performance increases up to a certain point, and then when you use only HBM, it decreases. So, which is initially very counterintuitive, that why when I use only HBM, my high bandwidth memory, why my performance is going down, why do I have a peak in between? The reason for that is, when you're using only HBM, you are not using DDR at all. It provides you some bandwidth which is less than the HBM if it is and you are losing that bandwidth. So a peak performance point would be when the data is divided among these memories in the ratio of their bandwidth, and other researchers have also found similar findings. So this was kind of like so we are on this right track. We are developing, the code is bug free. Does it, any questions on this? So we are changing the access ratio by changing the amount of data we are putting in HBM versus DDR. So one means entire footprint of my workload is in HBM. So if my workload has 1 gigabyte of data, all data is in HBM, and this means all my data is in DDR. 0.5 means 512 megabyte is in HBM, 512 megabyte is in DDR. Intuitively, it makes sense. If I'm using higher bandwidth memory, my performance should be higher. But the peak performance point is in middle, which is basically if I use only HBM, I am not utilizing the bandwidth of DDR at all. Like, consider you have 8 pipes, 6 pipes are coming from DDR from HBM, and 2 pipes are coming from DDR. If all your data is coming from just thus these 6 pipes, you're not using those 2 pipes at all. So that's why when you use only DDR, you lose performance, or you only HBM, you lose performance. So it's actually very tough. Like IIT Kanpur, there is a paper in HPCA which from IIT Kanpur that finds the right mix. It also depends upon the page characteristic. But what I did is I didn't pay attention to the page characteristic. I randomly picked pages so that I don't give preference to any page, and I varied the access ratio by varying the amount of data. So that's what I did, but you can do better than this by considering access pattern, bank level parallelism, and many other things. It's a very complicated problem, and there are also papers which try to apply AI to find the pages. Like you can even have, like, if I have P1 next to P2, or P1 and P2, and there is another page in between, the performance will change based on what addresses are coming to the memory controller and coming in the access pattern. So yes, it's an opportunity, I would say, for research. Any more? Yes. So with MCF, I worked with 16 gigabyte, and we found similar trend. If it can fit in your entire memory space, like HBM plus DDR, whatever the capacity is, it should be more or less similar trend. But yes, if it cannot fit and it's going memory, there are swaps happening, then it will be different. But that's my intuition, that it should stay the same, more or less. But we wanted to see performance and reliability together. We take the failure probability numbers and we project it here. It's just a 2D mapping of those numbers. So this is how the failure probability is varying in week 0, in midweek, and in final week. So we can see that in the initial week, even if the user is willing to lose some performance, like from the peak point to this point, I am not gaining much in failure probability. I am not able to reduce failure probability a lot. But in midweek, if the user is willing to give up some performance, then I am gaining something in failure probability. My failure probability has reduced, and then the same is in the final week. And this is also dependent upon your workloads. Like the results you see are for Cactus, but for medium bandwidth and high bandwidth workload, this curve and these numbers will be different. And the reason for that is like the high bandwidth workload will be more sensitive to the access ratio change on both the direction. If you change the access ratio away or from the peak performance point, your high bandwidth workload will be affected more than your low bandwidth workload. So it makes sense, like based on different workloads, trying different techniques and doing this in software gives you more flexibility. So these are the takeaways. Lower access ratios can result in greater reduction in failure probability in mid and final week. Low bandwidth workloads such as Cactus could gain more in reliability without losing a lot in performance compared to MCF, which is a high bandwidth workload. So this led us to maybe try an aging aware access ratio control mechanism. Currently Linux distributes pages half and half until HPM is full, and we implemented a technique which, as the system ages, changes the allocation policy. So basically we let the system run at its peak operating point in the beginning, and as system hits a user defined level of failure probability, we start cranking down the access ratio, and we will see a drop in performance when we do that. And when the performance performance loss hits 10%, we notify the operator that it's time to go replace the DIMM or the socket in the case of 3D die stack memory. And again, these numbers will be different for different workloads. Like for example, MCF will get the most performance degradation, as we see here. So this brings me to the closure of the first half, that is permanent faults in memory. And like recapping it would be like, we see that failure probability of an HMA system depends on memory type, error correcting code, and its age. Because the change in failure probability is dependent on workloads and its age, we need an aging aware access rate control, and an access rate control mechanism can get you sustained and more reliable operation for a longer period of time without needing a need for replacement quickly. So this brings me to the end of the permanent faults. Now I will be touching transient faults. And yeah, any questions? We just use these three, but in a transient fault study, we use like 11 workloads. We use workloads from DOE, proxy apps. So we increased our workload set, but we didn't use, machine learning and cloud workloads. So we use spec workloads, but we use like 11 or 16 of those. So in transient, but for MEMSIS, I would say we could get away with just using 3. So that was the case. So I will go to the transient faults. So keep in mind, now we are talking about transient faults, not permanent faults. Until this point, I was talking about permanent faults. So I will be talking about how do we. So and one other point to notice is, until now I didn't take into account the effect of data on faults. I was just moving pages here and there, and no matter what page it is. But now for transient faults, and you can do that for permanent faults because it's because it's long transient faults, things are happening very quickly, and you need to know more about the data as well. So we used AVF for that, and then I will discuss some of the profile guided placement, dynamic migrations, and program annotation based placements. This will be more clear as we go on through the slides. So again, the goal is we have a heterogeneous memory architecture. That is, we have die-state memory to repeat again, and an off-package GDRX memory. We want to move hot pages to HPM, but not just hot. We want to move hot and low vulnerable pages, like low risk pages, which have less tendency of encountering transient faults. So we have a way to define hotness, but we need to find a way to define what's low risk, what page has low vulnerability. To do that, we used a technique called AVF. It's architectural vulnerability factor, and AVF is nothing but a probability of like how vulnerable my bit is based on the read and write patterns. Like for example, here, if a particle strike happens here or a bit is flipped here, these two reads become vulnerable, and the bit is exposed to a transient fault for TR1 plus TR2 divided by total amount of time. However, if there is a write, now my bit is vulnerable only for TR2 divided by T total amount of time. So as you see from this slide to this slide, same access pattern or same level of hotness can give you two different vulnerability to transient faults. So that was our intuition when we started exploring that, and we wanted to see that. We should be able to find hot pages which are less vulnerable or low risk, because if all hot pages are high risk, we don't have a good memory to put it in the system that we have right now. So before I move forward, I would like to define a few more terms. So AVF of a structure MI is just the summation of the vulnerability of all the bits divided by the number of bits in the structure. And failure probability, as I discussed before in the previous work and in the initial background section, is the same, is the raw failure probability or the raw fit rate. However, AVF is just scaling this failure probability by AVF, which is taking into account the data effect into it, the read and write access pattern and the distances between them. So this is basically the probability of uncorrectable hardware fault, and we are scaling this number by AVF to get observable uncorrectable errors in software. So the goal is to find hot and low risk pages for HPM, and we have HBM which has high bandwidth and low reliability. So the ideal candidate for this memory would be hot and low risk pages, and for DDR would be cold and high risk pages, because it has lower fit rate, lower failure rate, and higher and stronger error correcting codes. So again, we wanted to find out that in real workloads, are hotness and AVF correlated, because if they are correlated, we won't be able to do or progress with this idea any longer. So we took a workload, and what you see here is hotness of top 1000 pages arranged in a decreasing order of their hotness, where hotness is just access number of accesses, that is read plus writes, and AVF is as computed through the equation that I showed before. And you can see that the correlation coefficient between hotness and AVF is pretty low, and there are hot pages which have very high AVF and very low AVF as well. So where AVF is the risk to transient errors. So these are my pages which are ideal candidates for HBM. So we did it in simulation. However, in reality, if you want to implement an actual system, doing AVF calculation, counting all the reads and write and the number of cycles in between them is like impossible. The counter overhead will be too big. So we need to find a proxy to AVF, and that we found out using write ratio. So the intuition is if a page has more writes than reads, or write to read ratio is high, then it's low risk page. Uh, 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 so that's what you see here. We have AVF, page AVF, and the write ratio in blue, and we see that there is an inverse correlation between AVF and the write ratio. If the write ratio is high, we have kind of lower AVF. So we use this proxy to find pages which are ideal candidates as we do our experiments. So the takeaway from this slide are hot pages could be high or low risk, and page hotness and AVF are not necessarily correlated. Writes, reads, and write ratio could be a close enough proxy for AVF or finding risk. So we tried different placements, and what you see here is a graph with different placements for one workload. I will show more workloads later, and you see performance as IPC, and you see soft error rate on the left side. So what we want to do is we want the bar to be as high as possible and the soft error rate to be as low as possible. So this is the only DDR case when we only have DDR, and the soft error rate of course is very low because it's a very reliable memory. Then if we put all the top hot pages in HBM, we have a HBM of 1 gigabyte. So we select all the top 1 gigabyte of hot pages and then we put them in HBM. So we see that we have increased the performance, but soft error rate has also gone high. We can do least hot, but that brings it down. But the thing to notice here is that we can try like least AVF, put the least AVF pages in HBM. That brings the soft error rate down, but it also brings our performance down. And we see that there are pages which can be there are pages which are hot and low risk, and we wanted to find that. And then using these heuristics, we were able to find those pages. So this is write ratio, where we get, so this is static oracular based. So we get the read write count for all the pages, and then we select the top pages with top write ratios, and then we put them in HBM, and then the rest of the pages in DDR. So you see with that we were able to get some performance, and the soft error rate is still down. However, write ratio is not giving enough weightage to hotness. So we tried this second policy, which is write square to read, and so you can see that while write ratio is unitless, write square to read ratio has a unit of hotness. So it's still giving preference to writes, but it's also giving preference to hotness. So the takeaway from here are that both IPC and soft error rate can be optimized, and there can be a placement of pages which will work for both performance and reliability, and we just need to find these points. So for this work we used again Remulator, and we extended it to do the data vulnerability calculations using AVF, and we again use fault sim for failure probability. We used homogeneous and mixed workloads, 16 core multi-programmed, and from spec benchmark suite. We created mixed workload because that's what a system would be running ideally, like mix of different workloads. And we show IPC and soft error rate for different placement averaged over mixed, homogeneous, mixed, and all workload. So these, I know these are a lot of graphs, but stick with me. So what you see here is IPC, which is performance, and in red you see soft error rate. Again, we want a bar to be as high as possible, and this triangle should be as low as possible. All these numbers are normalized to the performance focused numbers. So the one here means the peak performance, and the one here means the soft error rate of peak performance. So we want this bar to be as close as 1 and this triangle to be as far away from this dot as possible. So when we do the AVF focus placement, we are able to reduce soft error rate by 5x, but we are also taking a big hit in performance. The right ratio placement, being able to recover some of the IPC loss. However, the reduction has reduced. And the loss in performance is basically because it's not giving enough weightage to the hotness. So then we try right square by read ratio, which has reduced the soft error rate by 1.6x of the peak performance soft error rate at a very marginal performance loss of 1%. Now here we will see in more detail like what's happening when we select when we do an AVF focus placement or when we do a right square by read ratio based placement. So what you see here is for a homogeneous workload and a mixed workload, a scatter plot where each dot is a page and the x-axis is AVF and y-axis is hotness. So for each page we calculate its AVF, which is the risk, and its hotness, and we plotted it on this scatter plot. So you see here is that when you need to do an AVF focus placement, you are selecting pages from this side. So get me the pages which have least AVF. In process of happening that, you might end up selecting a hot or a cold page if you're only doing placement based on AVF. For performance, you're selecting pages from the top. However, you might end up selecting a very hot high risk page or a low risk page. Ideally, you want pages from this quadrant. So that's what right square by read ratio is doing it for us. Also, you see that the mixed workloads are losing more performance when you do AVF focus placement. And the reason for that is that mixed workloads have more variation in their hotness and their AVF characteristics. So when you select, when you do an AVF focus placement, you are selecting the least AVF pages, least risky pages for your HBM, and the variation between the hotness levels of these pages is like 0 to 6,000. While for homogeneous workload, this variation is not a lot. So you run into less risk of selecting a very cold page is to very hot page when you do a least AVF based placement. So that's the reason for that. And but until now, we've been doing like kind of an oracular study. Yes.
So when you say the software rate, my question is, can you not include the error correction from the software rate into consideration of the performance?
So no, error correction is included. Like after applying ECC, these are the soft error rate is basically the error rate of uncorrectable errors after applying ECC. So it's software observable error. If an error is corrected by ECC, it won't be coming to the equation I showed you, like the failure probability into AVF. So the failure probability has included the raw fit rates plus fault sim applies the error correcting mechanism and gets that number for me there, and then the AVF gets me the access pattern and the amount of risk that's there in the data. So this was all oracular. We ran it and we find out the placement, but we wanted to find something dynamic. So for that, basically, we wanted to implement a dynamic mechanism which, as the program runs and different program phases might have different characteristics. So based on that, we want to find pages for different phases. So a performance-focused dynamic migration scheme would be if we have HBM and DDR in my system, move hot pages to HBM and cold pages to DDR, while a scheme that takes into account both reliability and performance will be move hot and low risk pages into HBM and cold pages back into DDR. So we used the knowledge we developed from our static oracular studies, that instead of just taking read plus write, also take into account these write ratios for finding the low risk and high risk pages. So we implemented a performance focused migration scheme using full counters where we need one counter per page, and we needed 2.4 MB of counters for our memory system, that is 1 gigabyte of HBM and 16 gigabyte of DDRX. And we compared this implementation with a full counter with reliability based migration, where now we need two counters basically for each page. For performance we just need one counter because we are accumulating reads and write together, but for my reliability heuristics I need read and write for every page separately. So now we need two counters, so our counter overhead is double. We were able to reduce the software rate, but we suffered 6% of performance loss, which I believe is good enough. It was good enough for HPCA, so it was all right. We got rejected in micro, it was 11% then. But the counter overhead is still a lot. 8.5 MB of hardware overhead is not acceptable, so we try to reduce it using a technique called majority element algorithm. I won't be able to go into detail of this. This is again an HPCA paper where instead of counting the whole thing, they keep the counters for just like 32 pages or 64 pages, how many ever they wanted to move. And if a page becomes, if they have a list of these 32 or 64 pages, and if some other page becomes hotter than these existing pages, they bump out a page from there. It's not exactly like cache replacement as it sounds like, but it's more detailed, but it's somehow very simple that it has a very low counter overhead. So we modified these counters to include both hotness and reliability, and we see that there is a reduction in software rate by 1.5x compared to the peak performance case. But compared to the peak performance case, we lost like 5% or 4.9% in performance. So we also thought that this can be realized using programmer annotations. So if we could find out in our data sets or in our workloads that by just annotating a couple of data structures, we were able to find almost 512 MB of hot and low risk pages. So we did that. Like for most benchmarks, if we annotate just one program structure, somehow we did it ourselves, but if it can be done in compiler, that could be the next step. That can we find hot and low risk pages using some compiler technique. We marked it, like we hand marked them, and for most workloads by just marking in a very tight loop just one program structure, we were able to find, we were able to pin 512 MB of hot and low risk pages, and we saw an SCR reduction by this allocation, by a programmer annotation based allocation, up to 1.3x at a performance loss of 1.1%. Numbers very similar to the static one, because ultimately that's what's happening here, but the annotation is provided either by the programmer or by the compiler. So the takeaway is that a minimal programmer annotation can get you the static results without all the dynamic overhead that we have. So in summary, we saw increasing concerns in reliability and technology scaling and emerging architecture trends. Heterogeneity in memory architecture is not just in capacity, bandwidth, but also in their reliability. So there is a third axis to explore. I just said it, like we can exploit this third axis to increase or combat reliability concerns. We can mix and match these three axes. And I presented for permanent fault an aging aware data placement technique and an AVF aware for transient faults. So any questions on this? Mm-hmm. Yeah. So the migration overhead will be governed by the slower memory. and we took into account like 600 CPU cycles to migrate pages. So we did take into account. There can be a full uh, it, simulation, but what we did is we took our simulator and checked how much is the overhead of migrating one page, averaged it out, and included it every time we migrate. Um, there are more overheads. Every time the migration interval triggers, you need to empty your memory queue, because after migrations, if those requests are served, they will be bad. So, but that we include that overhead as well. But so when the migration interval triggers, empty the memory pipeline and then start migration and then start the next interval. Uh, yeah. And this there are lot there is a lot of migration work for performance, and they are all including that. And here, yes, if we would not have included like a big workload set, it would not have made it to HPCA, I'm sure. Uh, so I'm almost done with the technical part of it. I have one slide on, because I know the audience is the undergrad. So it's not like preaching, it's what I learned through a lot of beating in grad school, and it worked for me, so I would just like to share. Like ideas, you have ideas, you need to talk to other people, your colleagues, maybe in some other university, maybe your friend, maybe your mom. Sometimes if you try to explain it to your mom, they will give you some suggestion which you cannot think of. And start writing early. We don't write at all in academia until 48 hours before the deadline, and I think it's just terrible, because writing is the most important thing. Any paper that got selected, I have spent 1 month more on writing than on actually getting results. And I learned it the hard way. At companies like AMD, they won't let you work on any project unless you file patents, and I was not happy with that. But I think when I look back, it really helped. When you're writing, your idea matures, you're talking to the person you're writing to, and any crappy idea can be patent. So it was just taking me like a half a day or 1 day to write patents. I think it would be a good thing to include it in IITs. I think some incentive of writing patents. I think it does really help if you have some writing incentive. Implementation, master a scripting language and automate everything, like running an experiment, to grabbing those results, to plotting those results, and the graph is cropped up and get into the LaTeX folder and goes into the paper. Because believe me, your advisor will only work on your paper 3 hours before the deadline, and 2 hours before the deadline he will ask you to run a new experiment. So do that if possible, as much, and build an infrastructure you can test, and draw pretty plots. You will see that if you send a plot to your advisor, he will start replying to your emails. So and I think nobody, even reviewers, they don't read your entire paper. They look at the graph, they look at the abstract and the intro, and they know that they want to accept or reject it. So again, I use Python for this and for drawing the plot, so it makes it easier for me. So everything happens in the pipeline, runs and gets the results and draws the plot. And all the plots you have seen is through matplotlib in Python. You can use any other, but I think these were the things that helped me, especially graphs. I was drawing, instead of taking numbers, I started plotting and taking it to my advisor, and he was able to help me run new experiments. And like don't take it very seriously. This the next thing I'm going to say. I think if you see you run an experiment and your graph is going up and up and up, and there are no outliers, you probably have a bug. And if you have one inflection, start writing abstract. And if you have the reason for that, if you have another inflection, maybe a best paper award. So these are the people I interacted with in my PhD. Almost all the labs who were touching architecture at UCSD and AMD research. And thank you so much for having me here.